Hello and welcome to the ECG webinar, Can't Stop the Peering. I'm Mark Lindsay and I'm here with Brian Tate. I'll introduce him a little bit, but how are you doing today, Brian?
Doing well, doing well. Thank you. This is a very special day. It's a rare day that we get the 29th of February, so I'm enjoying the extra day.
That's right. Yeah, an extra day of the year and hopefully a topic that helps make outages on our BGP peerings just as rare as that. We'll get started as everyone is jumping in. Again, my name is Mark Lindsay. I'm if you can go on to the next slide. I'm a vice president here at ECG and a senior member of technical staff as well. And I'm here today with Brian Tate, my colleague here at ECG, another vice president, and also a senior member of technical staff. Brian began his work in telecommunications engineering, especially focused on transport in 1997, and has worked in IP-based data transport and networking since 2003. He's been working at ECG for much of that time that he's been in this particular segment of the industry. And we work together on design and operations of internet service providers and voice service providers. In particular, Brian's had consulting projects at a number of very large enterprises, government agencies, and then very many service providers, service provider networks. So welcome, Brian. Why don't you get us started and tell us what you're going to cover today?
Thank you. As Mark said, my background is in networking. I've had the privilege and the blessing of working for service providers, with service providers, even sometimes with helping them compete. And now I'm giving a chance to support them at ECG, and I enjoyed the opportunity to do that. So today we're going to talk about some peering, specifically between entities on the internet. And as you saw the title, it's Can't Stop the Peering. So with that, we'll jump right in. But before we go too deep, I want to talk about what is peering, just to make sure we kind of level set what we understand peering to be. We're talking about peering on the internet between different entities. And those entities are sometimes commonly known as ISPs. So another term for a non-backbone ISP might be a LIR, a local internet registry. There's some different terms, but the idea is that we're interconnecting networks of routers. And so really this is kind of the first cloud networking. So we'll talk more about peering today. We'll talk a little bit about history, and we'll look out for the pitfalls that can create outages and what you can do to protect against them. The peering we're looking at these days is kind of defined and codified in the Internet Engineering Task Force Request for Comments 4271. It goes back, about 2006, I believe. But BGP, that peering stuff that we're talking about, actually was developed way back in the 1900s, or 1990s to be more specific. There are good definitions in the RFCs for a lot of the terms that we'll use today, but I want to highlight a couple of them, like autonomous system, which is simply a group of routers all managed by a single entity with a routing policy so that they can exchange routing information, sometimes called routing information base or RIB, between the different entities. There's classically two types of peering with BGP. There's a gateway protocol for the interior, or IGP, and then there's border gateway. So if you think about the edge of the cloud being the border and the routers that sit on the edge of the cloud talking to each other, that's what we mean by most of what we talk about today when we say peering. And
So on this diagram,
go ahead.
On the diagram that you're showing, it looks like you have the exterior example up on that top left picture there, where you've got R4 in that cloud, sort of connecting outside the cloud. Is that an example of what you're referring to when you say exterior routing?
Yes. So the routers that are on the edge of the cloud are the ones that are actually involved with exterior border gateway protocol. I just wanted to mention that there's also the concept of exchanging routes between the routers within the cloud, or the autonomous system. And so this
Well,
routing
and
information, go ahead.
one thing I do want to say for everyone as we're coming along, you can go ahead and use the Q&A panel in Zoom for any questions that you have, and you can send those questions in, and then we'll have a special time to cover your questions at the end of the segment. So I apologize for the interruption. Brian, back to you.
No, I appreciate you highlighting that. So jumping back into the information that we're exchanging using the peering, it's information about routing. So we're talking about tables about, this network is reachable through this next hop, going back to basic packet level routing. But we're not actually focused on the packet level routing. We're tracking the information that helps develop the tables or the forwarding information base to actually send the packets. So when we're talking about peering, it preassumes that you understand a little bit about destination-based packet forwarding, but we're actually talking about exchanging information about that for how that's built. So we're talking about tables, and in networking, there's lots of different tables. Tables are recurring in lots of places, and one thing I want to mention is key to it is synchronizing that tables, or making sure that the tables in one router communicate to the tables in the other router with what they need and leaving out what they don't need. And that'll come, we'll talk more about that later. So recapping a little bit more of peering in general, we've got different types of peering participants, and you've got parties that actually participate directly in the peering. You've got some peering that are what I call upstream or transit, some that are downstream, like your customers. You have some that are sideways, meaning they're peers that are another internet service providers or large entities. Maybe it be a large business, a multi-location enterprise. And then there's also, I mentioned before, the internal peering that needs to be set up within your autonomous system. Autonomous systems are very important in being identified uniquely. And so when we're talking about peering, we're talking about unique IDs for each autonomous system, just like we talk about unique IP addresses on the public internet. One of the key things that you'll hear again later is making sure that things are unique and that things aren't leaked. A good tip is to always have a lab or a sandbox where you can test out your configuration changes or software upgrades so that you can make sure that things don't accidentally get passed between the autonomous systems. In the internet peering ecosystem, you've got other folks besides the parties that do the interconnection. You have folks that create the standards. I already mentioned the IETF, who creates a lot of the RFCs, is responsible for managing the RFCs that define the peering best practice. There's also regional internet registries here in North America, like ARIN, who handles ARIN.net, who manages IP resources, the addresses and ASN numbers that I talked about before. And there's also network operator groups. These, I think, are overlooked as a resource for education and technical relationships when it comes to peering. And I would encourage you, if you're not familiar with any of them, to look them up. There's a national one called NANOG, N-A-N-O-G, but they also exist at the state and regional level. Most recently, I ran into one in my neighboring state of Alabama. It's ALANOG, A-L-A-N-O-G, but they exist all over, and they're communities of network engineers, operators of ISPs, and even just professionals in the industry that are dedicated to advancing an open, a secure, and a robust internet. Last thing I wanted to mention was that there are peering databases, and they're participants in this peering ecosystem, and they help with things like validation and making sure that the right routes are accepted in certain places. And it deals more with relationships, but we'll talk more about that later.
So, Brian, I know you talked about one potential reliability tip there that you already gave us, which was doing some lab testing. on software transitions, and you talked about leaking. I know you're going to get into that more, but can you start to tell us more about some of the types of outage risks and maybe what causes those and what you could do to mitigate them?
Sure, sure. No, the first one we'll look at is something I call router memory exhaustion. It is historically, it's been something that I ran into a lot early on. I don't see it very often anymore, but there are still some layer 3 switches out there that if they're misused or used for the wrong application, you can still run into a case where the random access memory on the router can't hold all of the large amounts of routing information that's being passed between BGP peers. Normally, this information has to be stored in RAM and sorted through before it get pushed out to the forwarding information base that may be stored in TCAM or other types of addressable memory. You see a few different things on the slide that you can do to kind of address this risk, this potential outage. One is to limit the routes that you receive from peers so that even they may change their mind periodically and advertise more routes or less routes, and you want to put a limit to make sure you don't accept too many that what your hardware can actually handle or your router can handle. So some of that's knowing about the limits of your own routers in your autonomous system. Also, you can consider using a default route in certain places. Most folks have a default route for certain types of contingency and backups. But in some cases, if you're a small service provider and you're not multi-homed in a way that you need a load balance, a default route might be a good way to reduce the risk for a memory issue. There's also the summarization of prefixes, which is talked about, and there's not a clear practice on that. Typically, you don't advertise anything longer than 24 bits, network 24 bits on the internet on the default free zone. But you can actually change that. Maybe you filter out all the /23s and 24s, and that'll significantly reduce the size of the internet routing table that you're receiving from your peers and actually putting into your own memory. If you look at the graphic, this is just one graphic to illustrate the fact that at this point in 2024, there's in a lot of peerings, there's over hundreds of thousands of IPv4 routes. And despite a lot of efforts for aggregation and consolidation, it's actually getting worse, although some people are saying it might be stabilizing out as more folks move to IPv6. There's still a lot of Wild West in terms of trading IP blocks, and they pop up in different places, creating a bigger routing table. You can track them with, there's several folks out there in the industry that are tracking it. The regional internet registries like ARN or I found a useful article at Asia Pacific, APNIC, and there's a few other things. If you just Google for it, look for peak IPv4 routing table size. So this is still an issue. I ran into it most recently looking at some Nexus routers. And Cisco Nexus routers aren't the obsolete iOS routers of 10, 20 years ago. So it's still a relevant issue. So consider upgrading hardware if you need to support the growing table. Also, some routers are becoming virtualized. So you may just have to add computing resources, which will help you scale better there. There's a few considerations to think about in IPv6, where now you have even more routing information exchanged. Excuse me, but it tends to be better aggregated. It's more efficient in IPv6. Excuse me. By the very nature of the prefixes there. Another outage risk that we talk about is inactive routes. Inactive routes are routes that you think are received, accepted, and should be in use, but it turns out they're not actually in use. And it may vary from router to router within your autonomous system. So one of our telephony and internet service provider customers, they reported an outage after they had a fiber cut on one of their 2 upstream transit providers. They were multi-homed, they were actually dual-homed, and so they thought they were safe. But what happened was some of their routes, including a default route from their backup provider, it wasn't properly originating the routes that it was advertising. The result was that the local peering router, what I'm going to call router 1, Juniper Edge 1 in this example, which has been sanitized, it received and could use that router, I'm sorry, that route locally for certain things, but it wasn't passed through the interior gateway protocol. It wasn't passed to the router 2. And so router 2 only knew about its upstream peer. And when router 2's upstream peer dropped, it meant that none of the router 2, router 3, router 4, any of those routers had a way to reach the rest of the internet. And so it looked strange because there were some customers that could still reach the internet because they had a route out, but then a lot of the other route, because the default route was removed, a lot of other traffic was dropped. We worked with the backup transit provider and helped them understand more about how to properly originate the route in their route map. And it has to do with a BGP attribute called origin. And you can see in the slide, there's highlighted in yellow, the inactive region for that. The inactive reason for why that route isn't active is because of the origin was what's considered unknown, or so that value could be 0, 1, or 2. It was 2. And so that's what results in that question mark you see there. Once it was fixed, then it looked like the other route that has the I, and that was mean this route has been originated locally. You tend to see this more often on directly connected peers where they're originating routes within themselves instead of passing along through transit. So it just happened to be a slightly lower quality backbone upstream provider that hadn't made sure they were implementing all the best practices. You also see something else about the peer highlighted in orange, that their router ID in peering was not a unique router ID. They chose to use RFC 1918 space as the router ID. So it's not strictly speaking going to cause any problems, but it kind of showed some of their naivete in setting things up, and it led to kind of a flag of, you know what, this problem might simply be a tweak that needs to be done in the peering router policy. It turned out it was not just the default route, but that was where it was most obvious. So we can avoid that by making sure we test fault tolerance. Just like you see highlighted in the bottom, make sure you test redundancy. And if you've tested it once, things change very dynamically. Route maps change, configurations change. Your upstream peer, or maybe your sideways peer, they do router upgrades and they do software upgrades, and sometimes things get hung. So it's good to do periodic tests. Make sure your fault tolerance is working periodically. If you can multi-home with more than 2, then it makes it much easier and less risky to test, because you can test taking down one peer at a time. And so those are some of the approaches you might do to mitigate that risk.
So let me ask you about that. So a test
Sure.
in that case, a fault tolerance test, what would, can you just tell us just briefly what that kind of procedure might be?
Sure. So because this has to do with how you send traffic out, meaning it's your routing table, then what you're trying to make sure is that you're able to see an active route using a show route command, for example, like you see in the Juniper syntax or the Juno syntax here. Make sure there's a route there. Or from a high level user base, make sure that you have connectivity outbound so you can reach, say, a Google server, or you can ping out to a web server. And then check to see which routes in the route table you're actually using to get to that destination.
So, and I think this is probably an important enough question to a clarification to go ahead and jump to real quick. One of our viewers, Ed, said it sounded like you made a suggestion about filtering out /24 routes, maybe kind of a blanket basis. And his concern was, well, of course, there's a lot of service providers or organizations that are advertising their multi-homes and they're using /24s. Are you saying that generally filtering at /24 or more specific, which is in /24, what we really mean is a block of 256 addresses. So that /24 refers to that address length. But is that something that you would want to do universally, or kind of can you give feedback for Ed on that that concern that filtering /24 isn't it could potentially have an impact for a lot of organizations in that position?
No, that's a good point. I don't think I was clear when I was talking about it. This is one of many approaches to try to deal with the risk and to try to mitigate the total service outage that could happen if you run out of memory on your router. It is not, it's more that what I suggested in summarization, that's like a stopgap. That's not the first thing you would do. Filtering out routes will, unless you're a small provider where you have few upstreams, it's not going to be a good approach, because you will lose optimization, you will lose redundancy to certain networks. In fact, some places you may not know how to get there at all. It depends on your routing policy internally. So that's a good point, Ed. I don't recommend doing that. That's why there's a lot of differing opinions about whether or not that should be even considered as an option. But I think in the middle of the night, when your router's down, that's one way to get your router back up. And then you can deal with optimization, hardware replacement, increasing the computing resources to your virtual router, or something that's more permanent.
Right. And even then, if you did a filter and you had to discard routes, like you're saying here, where you're doing filter, you still have to have you have to have an alternative. So you have to have a default route. And so there you completely lost, like you said, your optimization, but you have to, I think as Ed is pointing out, well, you can't just like black hole that part of the internet. You have to have something in. So a default route through one of those providers, or maybe both, would be if you've got, two upstreams, for example, or two peers, that would ensure that you still have the connectivity, even though it's completely unoptimized. Just basically, you're just arbitrarily selecting one of those outbound routes. So there's kind of more to it, to that kind of procedure than just kind of let's throw it away. So that's a really good question. Thanks, Ed, for highlighting that.
Now we're going to move on to why it's important to know what you're importing. We've talked a little bit about this before, but at that border between you and the rest of the internet, or a peer that's advertising how to get to its networks, it's important to make sure you filter. I've seen cases also where a downstream customer mistakenly advertises things that will cause problems. So this is just kind of an introduction to talking about filters and how they can help us with making sure we don't get bad routes. Bad routes come from a few different places. A lot of folks characterize them into bogon routes or Martian routes. Bogons are bogus networks. Martians are special use reserved network addresses that shouldn't ever be seen on the public internet. So we have several different RFCs that define them. There's also some protocols in IPv6 that define things where it creates addresses that might be used for interoperating between, say, IPv4 and IPv6, but you don't want to see them on the internet. It can cause problems. It can create security risks and loopholes for malicious attackers. So again, examples for Martians might be things like loopback addresses, 172.x.x.x addresses, also RFC 1918 addresses, things like 192, 168, x.x. Those addresses are considered Martians and should not be seen as being accepted across external border gateway protocol sessions. Bogons are a little bit different, although sometimes they do tend to get lumped in together, especially for configuration convenience. Bogons think about them as the dark corners of the 4.2 billion possible unique IPv4 addresses that are out there. Granted, not all of those are public, but there are some that are still not yet allocated by registries. They're not actually lit in terms of they're not actually in use and not being advertised. There's some parties out there in the industry that will help you keep track of which ones have been allocated by Aaron, by AppNet, by RIPE, and help you create filters so that your routers know, hey, I shouldn't accept routes for these prefixes or these particular remote networks. And that can help with IP space hijacking. which we'll mention again later. At best, they cause unexpected problems, but they certainly used by cyber criminals for exploiting IT resources and software bugs. So filtering them out, as we said before, is just good practice. We'll look at a few examples of how to do that. But overall, I want to encourage you to be a good neighbor and work cooperatively. So when you create filters, it's good to communicate with your peers saying, these are the routes and prefixes that I expect to see from you. This is what I expect to advertise to you, and have a conversation to make sure that the peering is set up correctly day one. You don't want their filter to accidentally be missing one of your networks that you need them to provide connectivity for. So be a good neighbor and don't in the peering. IPv6 stuff is the same concept applies there. So here's an example of Cisco iOS prefix filtering for Bogons and Martians. You'll see some of the example addresses. You create a prefix filter, a control list, then you import that into a map, and this is a very simple route map here. But you can have multiple prefixes specified in the map, and then that gets applied to an interface or a peering with a partner on a BGP session. So you got the list, you got the map, and you got the session. You've got something very similar using a Juniper router or Junos, where you create a route filter list. It gets applied to a policy statement, and then you see that applied to your BGP group or your BGP peer session. One more example we'll show you. It comes from Alcatel-Lucent. These are far less common in North America, but we've got an example here on the left of how you might do that in IPv4, and on the right, how you might do that with IPv6 Bogons and Martians, which we haven't talked a lot about. Again, the addresses, some of the addresses aren't, this isn't a complete full list. These are just examples for reference. There's one thing I'll mention on the IPv6. You'll see an extra entry in the policy statement called trusted v6, and it uses another prefix list other than the Bogon one to give an example of how you can explicitly allow traffic just as easily as you can explicitly deny traffic from different networks, or about, excuse me, I said that wrong. Sometimes I go back to thinking about routing instead of peering. In peering, you're exchanging information about routing. So you're not actually making direct changes to your routing table. You're changing what's accepted or not accepted in exchanging that routing table information. Some of these policies are default deny, some are default accept. So be careful in whichever routing operating system you're using, and know where you should be complete or where you don't need to be complete in specifying a list of IP networks or prefixes. Another outage risk that you run into still with BGP peering is the physical layer, or the layer between what's operating BGP, which is really more of a layer 3 type of a protocol. You still run into problems with the data link and the physical layer in the OSI or TCP/IP model, depending on which you prefer in thinking about networking. And in this case, an ounce prevention with the physical cabling between routers, whether it's copper or fiber or whatever it is worth many pounds of remote access cure in the middle of the night. Sometimes it's not a complete failure of the physical layer. Sometimes it's something flaky. Not all regression testing or reestablishing a baseline. If you don't do regression testing, if you don't reestablish a baseline for like optical receive levels after a maintenance, maybe you replace a fiber module, maybe you replace a fiber cable, go ahead and baseline. And if you have as-built documentation, make a note that can be referenced by others of this is what's the normal receive level, this is the threshold, and it helps with troubleshooting later. Also, develop good working relationships with on-site, hands-on, remote hands-on folks. If you don't have a technician on site or you can't get one there quickly, that'll help make sure that cables that are custom made are crimped well, they're verified, In the case of copper, make sure all 8 pins are crimped properly, especially now that we have 1,000 base TX connections, and even faster than that with 10 gig connections, interconnects, and 100 gig. So it's not really about the speed. It applies everywhere, and we still see some of those as causes for outages in peering. Also, I want to mention data link. Although much less common, it can lead to IP peering outages. So I spent a lot of time troubleshooting layer 2 before I got to layer 3 networking in my career. And I got to see a lot about how layer 2 loop prevention protocols can sometimes get in the way when they're trying to be helpful. A lot of people have war stories and mixed feelings about things like spanning tree or ring type of protocols, ring protection. And I'd say just be careful with those. With direct connections between peers, like direct physical connections, that's a non-issue. But there's places where you can peer more efficiently with peering exchanges where you would connect to a switch or on multiple switches, and those switches are connected to other peers. And so for the same physical cable or dual cables, if you do link aggregation or however many cables you want to aggregate together, you can have cases where things don't get configured at the layer 2 level, and it can affect one or more of your peerings through that common switch fabric. So layer 2 is still important to know, especially in internet exchange networks, to make sure that you don't have sessions that end up flapping or bouncing, or somebody plugs in a switch and suddenly becomes the root of the entire spanning tree and drops several of the redundantly cabled peers. There's something called dampening that we'll talk about later, that it's not talking about the physical layer, but the concept I feel like still applies here, where if you can put in policies that make sure that you have stability with your peers, then that can overall keep you from having outages and have a more robust autonomous system on the internet. So we don't have time to go deep into security, but we'll talk about a few things. Security considerations in peering start with authenticating your neighbors and your peers. Are they who they say they are? There have been cases where man-in-the-middle attacks or folks can try to, especially across multi-hop, pose as somebody they're not. So it's good to authenticate. Most commonly, authentication comes in the form of a password or a key. There is talk about other types of security mechanisms. Modern routers don't have as much problem with this as some of the old ones, but BGP connection requests are pretty common. Just like port scanning on the internet for hosts, you'll see BGP connects pretty regularly if you log that sort of thing. So it's almost like there's bots everywhere that are trying to probe for BGP weaknesses. And there have been some. I'm not familiar with any recent ones in Juniper or the major players in routers, but in some other routing protocols that are out there that are open, there have been some bugs that they're being exploited or have been exploited. So be on the lookout for that, making sure you upgrade your software. Securing the actual link with your peers can also take the form of doing IPsec. That's mentioned in some of the RFCs. So you encrypt the actual connection, make sure it gets rekeyed frequently. I think there's even some talk about using technologies like transport layer security or TLS to create encrypted connections between routers in a peering environment. And don't forget, always filter what you expect to receive from the peer. There's lots of standards bodies that write not just the standards, but best practice. So look for BCPs. And another tip, maintain your logging. That's how you can troubleshoot and prevent outages once they occur, or when you're trying to look for things that might be incremental and building up. We found a lot of issues through logging or root cause analysis from logging. But once you once it's happened, you can't go back and turn the logging on without having the problem happen again. So be proactive about logging, and try to stop that.
Yeah, Brian, that's an interesting point because I know the way that logging is handled on different vendors varies a lot. So, for example, I know on a lot of Juniper routers, logging's on by default. You can go back and look at logs for some a good period of time potentially. And whereas on Cisco devices, usually the logging seems to be generally pretty limited. It's a pretty small window, and in order to get logs, the typical practice I see with Cisco is you send the log somewhere else. Um, do you generally have a preference there? Would you just go ahead and set up all of the routers to send the logs to a separate log server? And do you have any good experience with certain kinds of log server situations where it's been really helpful? I mean, which technology you use to store the logs?
I don't have a one size fits all recommendation, but even on the Juniper routers, that what you get for free can tend to be too verbose to be stored locally for very long. So system logging techniques or centralized logging is important. Typically, network management tools that also do SNMP will give you some options there, and it kind of depends on your budget, depends on the scale. But definitely put that as part of your engineering design up front and don't wait until it's too late. And again, having a lab will help you fine tune exactly how verbose different modules of logging need to be, because you may care on one router more about the BGP type of stuff to a certain level, whereas another router you don't care as much because it's hardened or safeguarded in a different way. So it kind of depends on the network as well. One quick last thing about security, want to mention sometimes you're involved in a security situation in peering that can be difficult, because you may have multiple parties come to you and say, one may say, you're not advertising our network, or your peers you're not accepting this network. And a remote party may say, well, they don't have authorization to do that. So be careful in being neighborly and trying to authenticate not just your peers, but the prefixes that your peers are advertising, especially if you're going sideways or with a customer that says, oh yeah, I'm a middleman now for this other network, you need to advertise this prefix. Well, it's good to have letters of authorization and other types of documentation to make sure that that's not going to get you in trouble later. Hijacking of IP address space is still an issue. I know it was a high profile one that I saw in a write-up of a colleague where Pakistan advertised YouTube's IP space, and there wasn't enough done in the filtering to prevent that from actually causing an outage for customers trying to access YouTube content. So definitely put time in design and troubleshooting and planning in the security elements of your peering.
Yeah, and that particular incident had some serious downsides for the nation of Pakistan, because it effectively functioned as a denial of service attack against the whole country while they were advertising that. They were trying to do a government imposed content restriction, and they accidentally shut down the network. But they also interfered with YouTube for other countries that were not within Pakistan. But yeah, show us this example of authentication.
So here's a couple of syntax examples for putting in that password for authenticating your peers, as well as some basic BGP configuration for an external peer. But there's many other topics that we could talk about too, when in terms of mitigating outages, preventing interruptions to your in-services. I mentioned earlier about the quality of your transit carriers. It's important to vet them. It's important to make sure when you come up with a multi-homing strategy that you have that taken care of and addressed. Sometimes contingency plans are oversimplistic, and don't take into account if a network or a particular city were somehow subject to an outage, maybe a weather event, or maybe something else. So you may get internet service transit from two different providers on two different cables, and they both come into, two different towns in your area. But if both of them are dependent on a common peer, say in Atlanta or Chicago, or even somewhere in between, you might lose both of them at the same time. So we've seen bits of that, and you just got to be careful. BGP doesn't, it's not a shortest or fastest path type of routing. It also doesn't automatically keep you from, say two different cables in the same cable conduit issues. So be on the lookout for that. Make sure you design your route maps, your prefix lists, your policy statements. Make sure you do test those out. We've seen typos that have caused problems. I've made typos that have caused problems. Labs are good places to vet those out and make sure they're good before you put them into production. As you scale your autonomous system, as you look at fine-tune traffic engineering, you might use communities to help instead of using just straight prefix filters like we talked about before. That helps manage the routes that are going into your routing table. There's summarization and aggregation, both in and outbound. Some things to look at. Timeouts. So if a peer isn't responding, you can configure your router to do certain things and how quickly it does. There's also max prefixes. Going back to that first outage cause that we talked about, the memory exhaustion. There's some, most software now allows you to clear or reset things to apply configuration without any hit to your forwarding of packets. But historically, there were options, and still are some options for things that will do like a soft restart versus a hard restart on your peering session. So know the effect of configuration changes before you go into it. Be aware of BGP tools. There are route servers, looking glass, even web interfaces for you to verify not just that the routes that that you're receiving are same, but also making sure that the internet sees the routes that you're advertising. Because a lot of our conversation today has more been about how you route out, which is based on what you put into your routing table or accept into your routing table. But it's also important in peering to make sure that what you're advertising makes it not just to your peer, but past your peer in order for you to have the kind of connectivity that you expect. And so that's where it's helpful to use route servers and looking glass. There's some other tools as well that are graphical in nature and will map things out and will show your autonomous system number and the ones that you connect to, and then some of the backbone players so that you can see, oh yeah, I have a high degree of certainty that, I've got redundancy to Facebook or whatnot. And you can't always see, though, in some of those tools, like your direct peering, it's that sideways peering I talked about early on. So you have to check out the internet exchange that you're connecting to or your peer to know if there's a way for them to log into their router and read only and see how they're accepting your routes. Sometimes a peering exchange will provide a route view server that allow you to look at how you're advertising and how it's being accepted to validate that it's kind of like a packet capture at the BGP level to see what things you're actually doing to validate both directions of the peering. And then so that goes into validation and some more advanced security topics that we can talk about. But unfortunately don't have time to today. And then traffic engineering. Local preferencing helps with what I talked about, the internet seeing different networks, and it can be done on a per prefix basis. It's helpful for troubleshooting if you have a peer that may or may not be consistently passing your prefixes upstream. And then local preference for if you wanted to have more local control of certain routes and not just depend on the AS path length, which is typically what's used in BGP. I appreciate your time and appreciate the chance to talk about outage prevention with peering.
Yeah, that was really good, Brian. Thanks for that sort of broad introduction and then the detail that you went into. We have several questions that came in from our viewers I want to bring to you. And some of these will refer to some of the things you talked about earlier on. In one slide, you had a graph showing the IPv4 routing table, and with it kind of generally ticking up as even just over the course of a few months, there's still an ongoing kind of march upwards in terms of the number of routes that are being distributed in the public routing table. And so one question came in about the relationship of IPv6 to this. And so you made a reference to some concept that maybe this is stabilizing as more people move to IPv6. Can you tell us more about that? A specific question was how is it that when people start to use IPv6 more and announce more addresses there, that we would lead to a decrease in the size of the routing table? Can you just explore that topic a little bit more for us?
Sure. So IPv6, even though there's more bits, 4 times as many bits to represent an address, it's built so that it's not, you don't have variable length networks advertised the same way. And in addition, there's a lot more aggregation and auto assignment at the lower ends so without going into a lot of detail about IPv6 structure, it was engineered in a way in the early 2000s so that it would avoid some of the pitfalls of the routing table expansion of IPv4, specifically having the idea of fixed network sizes and the ability to summarize more easily the routing table information. And so we don't see, even though it's got many more addresses, it's not going to increase the amount of the routing information base that's passed around in peering sessions.
Okay. So this would be connected to, as there's effectively more activity happening there in the IPv6 space. As you know, mobile phones come online, they don't necessarily need new IPv4 address space if they're mostly connecting over V6 and then they're going through carrier grade NAT. So that's part of the reason those kinds of things would contribute to kind of a reduced upward pressure on IPv4 usage, I should say. Is that fair to add in there?
Yeah, I think so. That's a good point.
Okay, great. So let me ask another question that came in. If you had a routing table with a lot of static routes in it, let's say you looked at a router and it had hundreds of thousands of static routes that have been created, maybe because these are links to, managing links to individual customers who've been built up. Would that lead to router memory exhaustion?
I would say not today, not likely. It depends on the implementation. There are things you can even do to reallocate how memory is used within a router for different types of tables. And it depends on how many tables you have. It's common now to use the same routers to handle both what you would consider internet peering and also internal networks using separated virtual routing and forwarding instances or different routing instances that are separate from each other. And while they may all be completely separate in terms of the routing, you do run into contention for the same hardware resources to store all of them.
Okay. But you're saying in current routers of today, you would not expect in general that static routes would be a major contributor to memory exhaustion?
No, definitely. Yeah, not static routes, because static routes tend to be few and far between. If you're managing static routes, managing with static routes, then it quickly becomes very difficult and risky to do that, as opposed to using an internal dynamic routing protocol to handle things.
Okay, so in that case, so yeah, I think the common case where a lot of us in internet service provider networks, small medium ISP networks, we would have static routes would be, direct links to customers where we can define them. But what you're saying is like probably as you're scaling that up, you're going to move to something like maybe a route server, and then you're using a routing protocol to distribute those. So you're not manually keying in routes in a router. You're loading them into a route server and then they're distributed over IGP internally, but instead of in the config directly.
Right. So those type of ISPs are putting static routes in for non-BGP customer connections. And those static routes tend to be /29, /27. They get aggregated into something that will actually be permitted on the default free zone of the internet. But those static routes will never be able to show because they've got a longer subnet mask than what's permitted.
Gotcha. Okay. Thanks for that. Another question was basically just the word autonomous system that's used early on. Is there some other kind of system that's not autonomous? What makes a system autonomous versus anything else?
So testing my memory. I've not read the RFC in the way they explain it. I know it does a very good job, the original RFC back in I think 1995 that described it. But an autonomous system is, again, just a group of routers that share a common routing policy, typically are responsible and controlled by somebody that has certain IP resources, typically IP address subblocks. And so that's kind of like a business or a particular ISP or a registry. And that's autonomous in the sense that they can do whatever they want with that IP space. They can assign it to one customer, or they can black hole it, or they can do whatever they want with it. They're autonomous in that sense. But then when you cross that border, that's where you have the peering and that autonomous system, everybody has a unique ID. And originally it started out with being only 16 bits long. So you had 64,000 in binary, 64K possible BGP peer identities, but it turned out that there were actually going to be more folks wanting to do BGP. So they have later expanded that to 32 bits. So now in the same number of bits that identify an IPv4 address, that number of bits can be used to identify a unique player in the BGP field. So we went from 64K to over 4 billion possible people or autonomous systems interconnecting using peering.
Great. Yeah. So the autonomous system is so like an organization that's got a policy that they get to control their own policy is what I heard there, and there could be a lot of them, over 4 billion theoretically. Okay, very good. I'll get through as many of the questions that we got as possible. So one of the questions is there a particular router that ECG recommends? I mean, can you choose a router that is going to be good for 10 plus years, something you can just put it in and kind of keep it and maintain it? Is there hardware that goes that direction that you would say to a customer or to another engineer, this is the router for you for the next 10 years? How would you think through that kind of request?
Yeah, so that's a good kind of a request for a design, considering not just the BGP portion or the memory portion, but also what typically happens is you also have to consider the feeds and speeds, is sometimes how they say it for the particular hardware that you're selecting. So memory is certainly one respect, the resources you need, what BGP feature set it supports. But I tend to run into more router replacements, not because they've run out of the ability to peer, but because they've run out of enough ports or the right type of port or the right speed. And so now that we're seeing links at 400 gigabits per second and faster coming into routers, it's hard to say that if you go with this particular model, or at least with this vendor, that you're guaranteed to always be able to last, 10 years. Some of it's also how you manage, or not your routing policy, but your overall operational policy within your autonomous system. Do you prefer to have multiple routes? Do you like to build a resh? Do you want to have a route reflectors, or do you want to do each individual router peering on the edge? So a lot of its design as to what particular model. I think in North America, I see most often Cisco and Juniper as the leading manufacturers of the hardware, but they run lots of different models. Some that are better at switching, some of them that are better at just routing. And so you would have to aggregate physical links coming into them. It varies depending on the type of service provider you are, pretty widely.
So one would be part of that I heard, identifying the kind of the application where it's going to be. But a key thing that you mentioned in several different formats was basically the interfaces that you need. And so being able to say that the interfaces you need today for your business are the same as 10 years from now, that might be a tall order to be able to give that kind of certainty to know that you're going to do it. I know that there's generally been a lot of modular routers, but even them, they stopped making them and stopped making new interface types eventually for every modular router that allows you to plug in new interface types. Another question we got, that you mentioned on kind of the last slide, talk about kind of advanced topics. You mentioned community, BGP communities, and we just got a request. Could you kind of explain what that is and a bit about how that can be used?
Sure. So that's a community is an optional way of passing information about the routing information base between BGP peers. It's not something that I see a lot on the small, medium size, unless you're connecting to a one of the few key backbone providers that support communities. But if you're just peering, typically at the small, medium size or through a peering exchange, you may not run into communities. But communities typically look like an AS number with a colon and then a community number, and it's they can be defined by your peer as, this is default routes, these are partial routes, these are routes from this particular region. This includes international or European. And so you'd have to talk to your peer to find out exactly what you should configure to accept and then they would give you the ability in that peering session to exchange the information about the routing based on how that's set up. I don't think we have enough time to go much deeper than that at this point.
Right. Okay.
But it is a
great.
powerful thing.
Yeah. Thanks for that feedback there. So another question, if you were going to set a policy for prefix limits to prevent exhaustion, basically what you're going to allow in order to prevent exhaustion, is there kind of one best practice for that, or is there a general procedure that you would follow to kind of arrive at what the right limits are? I think basically the logic behind this question is, well, I don't want router memory exhaustion to sneak up on me. So I want to put some policies in place that are going to make the router effectively protect itself.
Sure.
How do you think through solving that problem?
Sure. Where I see it most useful is not on the transit connections, although you can certainly do that on a transit connection if you're not taking full routes. Full routes means you would get all hundreds of thousands of routes from your peer. If you were concerned about that, gradually sneaking up over time, you could just cap it at something. That's going to be more disruptive than if you put limits on a lateral peer, who maybe they only have 30 networks to advertise to you, and that you've had a conversation about the paperwork's been exchanged. These are the networks you should expect to receive from me. Putting something in there like a limit of 40 or 50 is a good idea, because if they have a mistype command or a router upgrade goes bad and suddenly they advertise to you full routes, that's where that prefix filter comes in. So it's not exact number. It tends to be on a per peer basis, and it's more useful in their lateral peers or your downstream peers who might accidentally increase above like 10s or 20s or hundreds of routes. and go up to hundreds of thousands. That's where it tends to be more useful in safeguarding your memory.
Gotcha. Okay. Well, we're out of time. Thanks very much, Brian. I appreciate all of your feedback. If you were on this webinar, then you'll get a copy of these slides. Appreciate all the questions that everyone sent in. Thanks very much again, Brian, and have a good day.
All right. Thank you, guys.